Okay, and that's what's done here on this slide. Okay, so you have the analytical solution for eta, for the sea level elevation shown at the top. You have your governing equations. You plug in the eta onto the right side of the first equation. Okay, and then you get a solution for the horizontal velocity component u. Okay, so the entire fluid moves at a certain speed either to the east, to the right, or to the left. This is the u, the velocity. It can be positive or negative, and it can be derived. So again, it's also a sinusoidal function, okay, because it swings between two directions, okay, has the same form, but you can also derive the speed of that flow. This u0, and the speed of this flow is related to the sea level elevation. Okay, so you have that here at the bottom. Sea level elevation square root g divided by the total volume. Okay, so if you create such a wave, you disturb the sea level, you can work out what is the magnitude of these horizontal flows that you get, oscillating horizontal flow. But you can do a little bit more even than that. You can also derive the vertical velocity. The vertical velocity, in effect, it's what at the very top moves the sea level upward and downward. And it's associated to a vertical velocity, but you can derive it at any location within the water column, and you can derive it from that local form of the continuity, this form up here. And it relates to any volume element that you grab, any little cube that you, okay? Because you have a solid seafloor at the bottom, so the vertical velocity has to be 0 at the bottom, and accordingly, because you have a constant depth, constant horizontal flow fields, the vertical velocity increase linearly with height. Okay, and this is sort of shown on this. Okay, so you can work that out. And then at the end, you can even produce a little animation. You can translate this into the movement of parcels. And I did that here. You can look at the movement. Yeah, this one is a long surface gravity wave, and this one shows you the analytical. Okay, maybe I do it again. Let's just go forth. Here it is. Okay, that's how it looks like. And this should be the reference for a numerical model. So now try to simulate this wave with a hydrodynamic model. You want to have exactly that solution. Not only the shape as so, but also the inherent properties like the phase speed. Yeah? Phase speed, square root, g times. All right, so let's do a little bit more about that. Well, the next part is actually an additional part, and we look at the interference between two waves, two of these waves. So what happens if you have actually two, not only one wave? All right, let's have a look at that.